is defined as that temperature whose black body, I mean, this is the equivalent temperature that corresponds to a black body at the same specific intensity. So if you have a specific intensity, you can rewrite, if you want, it's like a change of units almost. You can always do this transformation. This would be in Jansky's per sterad. And if you write it in terms of the Planck function, that gives you some temperature. And this is called the brightness temperature. So it turns out that when the medium is composed of thermal emitters, then they, I mean, the source function is the Planck function, and in the optically thick limit, the emergent intensity is exactly the Planck function. So you can describe the specific intensity in terms of the brightness temperature directly. But this transformation can be done in general. In general, then, the brightness temperature would depend on frequency, like we have here. The temperature, the brightness temperature would depend on frequency if it's just a change of units. But in the optically thick limit, this brightness temperature is constant with frequency. So in the limit of radio frequencies, when the h nu is much less than kT, so when we have h nu, the Planck functions, then the frequency much less than kT, which is the Boltzmann-Law times temperature, then we are in the Rayleigh-Jeans regime, and we can replace the specific intensity with this approximation. So this is the limit of the low frequency limit. And you invert this to obtain the brightness temperature. So basically, the brightness temperature is equal to the specific intensity divided by mu squared. So this is again the limit of low frequencies. So you can apply the Rayleigh-Jeans limit to the radiative transfer equation. So this was the version of the radiative transfer equation in terms of the optical depth, and you get that the gradient of the brightness temperature is minus the brightness temperature, so that would be the incident intensity, and that would be the emission coefficient. So I'll bring up equation 138. This is page 26. 138. Okay, is that right? So this is the equation, transfer equation, written in terms of the optical depth coordinate rather than the physical linear S. So we're at page 27 back there. And that is an interesting way to put things, because then we can integrate this equation and write the emergent brightness temperature from a uniform slab. So the way the book presents it is through the Rayleigh-Jeans limit, and we get to equation 162. And you can compare this equation with that. Let me bring it up again. So it's backwards again. So we could have gone directly there, actually, without the need to go back to the transfer equation. This one. Look at the first form. So the one on top here. So we have the emergent intensity from a uniform slab is equal to the incident intensity attenuated by the optical depth plus the source function, which is the Planck function for thermal emission, times this factor, which goes to 1 in the optically thick limit. Okay, but if you remember this this expression, it's the same as the one we're writing now. If you just apply the Rayleigh jeans factors of both sides. So you use this equation and go apply the Rayleigh jeans transformations on both sides. So okay, here we go. You just take the above equation, multiply by c squared divided by 2 nu squared k, and you get equation 162. So why is this so useful? Because it shows that in the optically thick limit, when tau nu goes to infinity, this is completely attenuated. The first term is completely attenuated, and the second term is well, the factor is going to be 1 for the optically thick limit, and you'll get the temperature, the medium's temperature of the material, right? So the emergent brightness temperature is equal to the temperature of the material in the optically thick limit, okay? In the optically thin limit, which is not, intriguingly, is not written here, I don't know why. So in the optically thin limit, you can imagine how we do the expansion here. We expand this exponent. So e to the minus tau nu, if you expand first order, is going to be 1 minus tau nu. Cancel that with a 1. And you end up with to first order well, I need to write it down actually, but suppose that there's no incident radiation, so this is 0, and then you'll get that the brightness temperature is equal to tau nu times t. So in the optically thin limit, you get that the emergent brightness temperature is equal to the optical depth times temperature. And if you increase the optical depth, then you have a maximum value, which is the temperature of the medium. So the emergent brightness temperature can be 0 in the optically thin limit. It's proportional to the optical depth and the temperature. And as you increase the optical depth, then the limiting value is 1. So 1 is the temperature, I meant. So the color temperature would be that equivalent temperature that joins two flux measurements to 2 frequencies. So you fit a black body, and the temperature of that black body would be the color temperature. I think you're familiar with that idea. And the effective temperature is when you transform the emergent flux from some body, and you write it in terms of the flux you would have if it were a black body, and that would be the effective temperature. So I think these are, I mean, unless you have any questions, is that clear to everyone?
Yes.
Okay. So now we'll describe the Einstein coefficients. And I invite you to make sure you understand the textbook. So for my part, I'll quickly go through my summary. In a discrete medium, the idea is that we describe the coupling of radiation with matter through radiative transitions. So, I mean, this is actually real life. Of course, you know that life is ruled by quantum mechanics, and everything occurs by transitions in the discrete energy states. And so the coupling with matter occurs to transitions between energy levels, and each of them has got a line profile which is parameterized as phi nu. And these line profiles are centered on the transition frequency in mu0. Okay. And these radial transitions are described using the Einstein coefficients. So those are familiar to you, I'm sure. You have this rate of probability of spontaneous decay. Then you have the probability of absorption per unit time per absorber. So where you have this B coefficient, and when you multiply the B coefficient with the integrated J, so I've put a dash on top of J to indicate that this is the mean specific intensity, but integrated over frequency. So that would be then the frequency average mean specific intensity. So it's frequency average because it's multiplied by the line profile, which is normalized. Okay. That would give you the probability of absorption or upward transitions per unit time per absorber. Okay. So meaning that the units of B times J, the units of this is seconds inverse seconds. And this other coefficient, Bj times J, is the probability of stimulated emission per unit time. So here I think I should also have the same average. I don't know why, maybe I forgot to put it, but this, I mean, the probability of stimulated emissions, we talked about it before, is written the same way as the probability of absorptions. So this should also be the average, actually. Okay, so I mean, you need to fix this. Okay. Maybe no, guys, maybe I do this straight away because afterwards I won't be able to. So okay, so that's what I mean. I just fixed it. So you see that the probability of stimulated emission per unit time per absorber is the same as the probability of absorption, but with the subscript I and J reversed. So instead of going from state I to J, we're going from J to I. And so the line profiles are described with the Lorentzians. We'll go through the theory describing the interaction of radiation with matter, and we'll demonstrate that these profiles are Lorentzians. And their width can be connected with this rate of spontaneous decay with the energy time uncertainty principle. Okay, so this the E is h nu. Okay, so delta E is h times delta nu, and the time variation in the upper state is going to be given by the I mean how can I explain this? This is the time the system spends in the excited state is going to be given by the rate of spontaneous decay. So if you have a probability of A to decay per unit time, then the typical time that the system is going to spend in the excited state is going to be the reciprocal of A. So that, when you integrate the probability over time, it's going to give you 1. And then, so that would be delta T. and that was 1 over A, and H is is and delta E is H times delta nu, and so you can get here from the uncertainty relationship that in the best scenario, delta T is connected with the width of the line. Do you follow me here, or because I haven't set up my tablet, that might take a few minutes or a minute. Do you want me to explain this more? Is this clear to everyone? Is it obvious?
Yes, this is fine.
Okay.
Yes, I think this is fine for me.
Okay, good then. Okay, so there is an exercise I need you to do, and that's showing that detailed balance connects the Einstein coefficients. So this is the relationship between the Einstein coefficients. So this is a super important exercise you need to do. We'll do it again when we describe the radiative transitions, including collisions and the possibility of masering or lasering. But that's a standard argument, and I think it's described in the textbook. I think yeah, that's it. So you need to understand this argument, okay? Make sure you understand this. It's called detailed balance. When we equate the number of upwards excitations to the number of downwards de-excitations. So the number of excitations must be equal to the number of de-excitations. If this wasn't true, then the level populations would depend on time. And so in steady state, it is necessary that this equality holds. Of course, we're not always in steady state. We could perfectly well not be in steady state. But here we're talking about microscopic quantities. We're talking about properties of the atoms, and they will be the same, those properties, whether we are in steady state or not, okay? So we can connect those properties in a specific case, which is steady state. And so from this equation, we obtain that we can solve for the mean specific intensity. And then we go one step further and say, well, what if we are in thermodynamic equilibrium with the radiation? Then the J constant is the Planck function, and the level population are given by the Boltzmann statistics. And in this case, we get the relationships between the Einstein coefficients, which I've got summarized here too. Okay. So of course, we're not always in thermodynamic equilibrium, and we're not always in steady state. But the relationship between those microscopic coefficients must hold always, also in local dynamical equilibrium.
Simon.
Okay.
So equation 1.72b says that the probability of spontaneous emission is bigger than the stimulated emission. Is a common spontaneous emission is a common process, no? Or more common than stimulated emission.
Why do you say that? And it's because you're guessing that this number is very large?
Yes, I was guessing that that number was bigger than 1. But there is a connection between the probabilities of spontaneous emission and stimulated emission.
There is a relationship, and in order to compare which is most important, you need to go here. You need to compare A, which is the probability of decay per absorber, with the probability of stimulated emission, which would be B times J. So if you have no incident photons, the probability of stimulated emission is 0. Okay. So in a discrete and isotropic medium, the radiative transfer equation in compact form, I think equation 26. This is equation 26. So that would be the way to write the radiative transfer equation with an emission coefficient and an absorption coefficient. So because this is a very phenomenological relationship, when we derived equation 26, we said, well, something must be emitting photons, and likewise, same something must be absorbing photons. And just these simple considerations lead to the compact form of the radiative transfer equation. And in the case of a continuous medium, we split the emission coefficient in terms of one that's connected to thermal emission, which are labeled ABS, and the other one, which is due to scattering. And we also split the absorption coefficient. This we cannot do for the lines, the second step. But the general form, the compact form, is what we can apply here. And we can see now that the emission and absorption coefficients are directly connected to the Einstein coefficients. So for the atoms, we will in general assume that the phase function is constant. That might not necessarily be true if you have a polar molecule, for instance. But even if it's not true for the water molecule, for instance, when you have a mix like water vapor, all water molecules are mixed in random orientations. And so on average, the phase function is isotropic. No molecule, then there's no preferred direction. This might not be true in the presence of a magnetic field, for instance, which aligns the electric dipoles of each of the molecules. Okay, so the emission coefficient can be written in terms of the rate of spontaneous decays. Okay, so this is how we write the emission coefficient for a discrete medium, taking into account the Einstein coefficients. Right now, we are just saying that this is how it is with some line profile. But when we will go through the theory of the coupling of radiation and matter, we'll see that this is indeed the case, and we'll prove this. Okay, this derives from Fermi's golden law in quantum mechanics, which I'll try to summarize when we come to that stage. But it makes sense qualitatively. Each quantum of radiation carries an energy which is given by h nu 0. Okay, so each photon carries an energy which is given by the difference of energies in the transition in the transition that is occurring, and that is energy is always the same because it occurs between different quantum energy levels. And those photons can be emitted in 4 pi solid angle in any direction. Okay, and we must multiply by the number of molecules that are in the excited state to know. I mean, the more molecules you have per unit volume, then the more you emit, of course. And by the probability of decay, so A is the rate of spontaneous decays, the number of decays per second. Okay. And last is line profile. So, this is the emission coefficient as a function of frequency. And so we need to convey the idea that away from the line center, there's no emission. On top of the line, there is a lot of emission. So perhaps we could model this line profile with a delta function, for instance. it turns out that when you go through the details, this line profile is actually a Lorentzian. Okay, you know, you've heard of the Lorentzian in different contexts, like electrical resonances or resonances in general, and this is more or less what's happening here too. So in the case of a discrete medium, this is also including the scattering term. Why do I say this? Because imagine that you have what's going on with scattering in terms of in quantum mechanical terms. You have a photon that's hitting an atom, and it's going to be reflected. So what does that mean in quantum mechanics? It means that the photon is absorbed and then immediately decays, and then the atom decays and re-emits the photon in some direction. So the net effect would be like a scattering, if you want. Okay, the excitation is described by this term. The absorption is described by the absorption coefficient, but the re-emission is described by this term. Okay, and the absorption coefficient then must be the sum of two terms. The absorption coefficient is the absorption part, which is how you remove quantas of energy from the beam or from the ray in terms of the density of absorbers in the lower states times the upwards Einstein coefficient, corrected for the rate of stimulated emissions. Okay, so because this this rate of stimulated emission is also given the an increase of radiation in the direction of propagation. Okay, so that would be when we talked about the absorption coefficient, we said that it could be negative in the case of stimulated emission, and this is the corresponding term. Okay. That's it for the line radiative transfer. Maybe there's something interesting to mention here that in the emission coefficient we have this. I mean, this the quantum of energy is what I'm trying to say here is that it's interesting to note that the emitted quantum of energy must be taken at the center frequency, even though the line profile depends on nu. That's interesting because we're saying that the emission at the frequency that's not on the center of the line is still going to be written as if the quantum had the energy carried by the center of the line. Okay, how is this? Well, again, that derives on the theory behind the coupling of radiation and matter. And when you go through the theory, the line profile is the Lorentzian, not nu times the Lorentzian. This is basically the short answer, that we need to go through the calculation to explain this. Okay. But qualitatively, this is a symmetric function around the line center, and each photon carries always the energy given by the line center, even though the emission is not calculated at the line center, but the probability of emission of such a photon decreases away from the line center. That's how it turns out to be. I mentioned that this is a very difficult time for me, so I'm sorry for this. This is the only difficult time of semester. It's not going to happen again. It happens once a year, and it's at the late April, where we all of us radio and infrared astronomers go crazy with ALMA telescope proposals. Okay, this is very important for me, for my students too, because we are all preparing what we will be working on for the next couple of years. Okay, so this is to say that I won't be able to do my lectures next week. I hope you understand that. I hope that maybe you'll take the time to go through this part of the textbook, which is the random walks. So please take next week to go through the random walks and start doing the homework. So please do the random walk 1.7 and the radiative diffusion. These are super important topics and difficult to understand. With this, we close the chapter on radiative transfer, and you can start doing well the homework for this chapter, which is doing the problems of Rabicki and Lightman. The week after next, I'll ask whether you have questions on this, and go through the rest of my transparencies to explain the solutions of the radiative transfer equations, which in my summary, I've updated the topic because by the time where the book by Rabicki and Lightman was written, there were some solutions were not known yet. There was some progress on this in the late 90s by a team of Japanese researchers, whose work went relatively unnoticed actually until maybe 2 years ago, where their work was remembered and applied intensively at the moment. So we need to update the textbook on this, and that's what I will do in what's left of this chapter. So please take next week to cover by yourselves what chapter 1.7 and 1.8 and do the homework. The week after next, we'll meet and discuss radiative transfer. I'll describe the rest of my chapter, and then the week after that, we'll do the first exam, which, as I said, is going to be like a homework, okay? And I'll give you references, so really, the exam is going to be about reading the references and writing the solutions, okay? But, so don't be scared by it. But you do need to be prepared by doing the homework I'm suggesting here. Okay, so please do the homework of resolving those problems. It's a bit of a pain, but it's important for your training. I can say even that the most important chapter of this course is this one, radiative transfer and this approximation we're looking at now. And that is probably the only important thing I have to tell you this semester. So please, take the time to do this homework and understand very well these concepts of the random walks and radiative diffusion, please. So with this, I think we'll finish today, and this means we'll be meeting again in 2 weeks. Okay, so not next week, but the week after. Okay, and I apologize for this, but I just don't have any minutes left. So. So, and before we hang up, please remember to contact Rafael Martinez, who is the TA, teaching assistant on this course, and is more than happy to help you out with the homework or answering questions. Okay.
Thank you very much, Professor.
Okay, bye.
Thank you.
Ciao,
Thank you.
Felipe.
Good luck with the proposal.
Ciao. Thanks.